section for these 20-minute talks. We're going to be hearing from Anderson Vera from Pohang University of Science and Technology. He's going to be telling us about a double Johnson filtration for the mapping class group and the Goeritz group of the sphere. Thanks so much for being with us, Anderson. Go ahead.
So thank you very much for the introduction, and thank you very much to the organizers for giving me the opportunity to talk here. So this is a joint work with Kazuo Habiro, and the subject of the talk is the mapping class group. So let us start by fixing some notations. So we denote by sigma the compact connected oriented surface of genus G with exactly one boundary component. And so here we have one model of our surface embedded in the three-dimensional space. And the group in which we are interested in is the symmetric group of the surface in the topological sense. So that is, we are considering orientation-preserving homeomorphisms, which are the identity on the boundary, up to isotopy. So this is the mapping class group of the surface. So this is one main object in low-dimensional topology, and we can study this group by using different kind of approach, but we are going to use an algebraic approach. So before this, let me recall that one of the main example of element in the mapping class group is the so-called Dehn twist. So we have a simple closed curve on the surface, and we take a regular neighborhood, which is an annulus or cylinder. And so the Dehn twist along the curve is the orientation-preserving homeomorphism of the surface, which is the identity outside the regular neighborhood of the curve, and inside the cylinder is a twist. So this is one of the main kind of elements in the mapping class group, and in fact, the mapping class group is generated by Dehn twist. And so, as I said, we want to use an algebraic approach, and so we are going to study this group by studying how it acts on other objects. For instance, we can consider the fundamental group of the surface. So this is since we have a one boundary component, this is a free group. And if we fix a system of meridians and parallels, so this is freely generated by the homotopy classes of these cubes. And if we consider the map, which take an element in the mapping class group and we consider the induced map in homotopy. So we get a map from the mapping class group to automorphisms of the fundamental group, and this map is well known to be injective. So this is the Dehn-Nielsen theorem. And so we can see the mapping class group as a subgroup of the automorphism of a free group. And by using this map, we are going to study also the action on some quotients of pi. So we consider the lower central series of pi. So this is the sequence of subgroups of pi defined as follows. So the first term in the sequence is pi. The second term, gamma 2 of pi, is the subgroup generated by commutators of length 2. So by elements of the form a times b times a minus 1 times b minus 1. And the third term is generated by commutators of length 3, and so on. So in general, gamma n plus 1 of pi is the subgroup generated by commutators of elements in pi with elements in gamma n of pi. And so these are normal subgroups of pi, and moreover, they are characteristic subgroups. So they are preserved by any element in this group. In particular, the action of the mapping class group preserves all these subgroups. So we can consider the action on each of the quotients. So for every n, we denote by rho n the action on the quotient pi over gamma n plus 1 of pi. So we can consider this sequence of maps as a step-by-step approximation of the map rho. And by taking the kernels, we can define some subgroups of the mapping class group. In particular, for instance, we can consider the kernel of rho 1. So this will give the elements in the mapping class group, which act trivially on pi over gamma 2 of pi. So this is the abelianization of pi, which is the first homology group of the surface. So the kernel of rho 1 is called the Torelli group, And this is, we can think in this group as the nonlinear part of the mapping class group. But we can consider also the kernel of the other maps rho n, and we are going to obtain a decreasing sequence of normal subgroups, starting with the Torelli group. This decreasing sequence is called the Johnson filtration. It was introduced by Johnson, and it was studied mainly by Morita. And the n term in this filtration is the kernel of the map rho n. So explicitly is the elements which act trivially on this quotient. And if we consider the semi-direct product, so this condition can be also written as a commutator condition. So what is the underlying setting behind this? So we have a group G, so in this case, the mapping class group, acting on another group K, in this case, the fundamental group of the surface, and this group is endowed with a filtration indexed by positive integers. So in the above case, we have the lower central series. So what we want to consider is a group, which will be the Goeritz group. I'm going to define in some minutes. And this group acts on pi, but now we are going to endow pi with a double index filtration. So we are in the same abstract setting, but we are modifying the filtration. And we want to use this to define a double filtration of the mapping class group. So we will start first by defining it for a smaller subgroup, the Goeritz group, and then we will extend to the whole mapping class group. And moreover, we are going to identify the leading terms of this double filtration. So let me say what is the double filtration of pi that we want to use. So we can define this in general. So if we have a group K together with two normal subgroups, X and Y, we can define what we call the double lower central series as follows. So K00 is the group K itself. And in this column, we consider the lower central series of X. And in this row, we consider the lower central series of Y. And now we fill this square here so we use a similar condition as in the case of the lower central series. So the term Kmn is obtained from the two previous terms by taking commutators with the base steps. So for instance, K11 is going to be the subgroup generated by commutators of len 2 with one element in X and one element in Y. K21 is the subgroup generated by commutators of len 3 with two elements in X and one element in Y, and so on. And so we want to consider a double lower central series of the fundamental group of the surface. And this allows us to introduce the Goeritz group of the sphere. So let me talk about this. So the mapping class group has a strong interaction with the topology of three manifolds. And from this point of view, we can consider the surface sigma as being the boundary, as being the part of the boundary of a handle body. So we consider a handle body of genus G is standardly embedded in the tree sphere. And this means standardly embedded means that the complement is also a handle body. So we have two handle bodies, the inner handle body and the outside handle body. And the boundary of these two handle bodies is given by the surface together with a disk. And in this way, we obtain two embeddings. So from sigma to the inner handle body and iota prime from sigma to the outside handle body. And by considering the induced maps at the level of the fundamental group and taking the kernels, we obtain two normal subgroups of pi. So we are in the setting to consider the double lower central series. But before this, so in terms of generators, what are these groups? So we have that the fundamental group is generated by meridians and parallels, Now this group X is going to be the normal closure of the meridian. So this is a free group, but it's not finally generated. So we have all the conjugates of the meridians. And similarly for Y. Then we consider the double lower central series, and we define the Goeritz group as the elements in the mapping class group, which preserve these two subgroups at the level of the fundamental group. And this condition implies that the action of the Goeritz group is going to preserve all the double lower central series. So this group is called the genus G Goeritz group of the sphere. And let me give some equivalent definitions of this group. So we may think of this group as the set of orientation preserving homeomorphisms of the triosphere, which preserve the boundary of the handle body and the disk up to isotopy. Or equivalently, we can see as the elements in the mapping class group, which can be extended to the inner handle body and to the outside handle body. And this is the same as saying that these are the elements in the mapping class group which preserve the standard Heegaard splitting of the triosphere. And so this group, we do not know if it is finally generated for genus greater than 3, but there is a conjecture called the Powell conjecture that says that it is the case, but it is still an open problem. We have some related groups. So we have the two handle body groups. So we can consider the mapping class group of the inner handle body. And this can be identified with a subgroup of the mapping class group. So these are the elements preserving the subgroup X. And we have the handle body of the handle body group of the outside handle body. So this is the mapping class group of the outside handle body. And this can be identified with the elements which preserve the subgroup Y. And these two groups act naturally on the fundamental group of the corresponding handle bodies, and we can take the kernels of that actions. And this gives us two groups, which are called the twist groups. So here we have the lattice of subgroups. So we have the mapping class group, the two handle body groups, the two twist groups, and we have the Goeritz group. And we know that mapping class group and handle body groups are finally generated. We also know that the twist groups are not finally generated. And for the Goeritz group, this is still an open question. So let me give some examples. So here we have three simple closed curves, epsilon, gamma, and delta. And the then twists along epsilon, gamma, and delta, these are elements in the twist group. T epsilon and T gamma do not belong to the Goeritz group. But if we take the product of T epsilon and T gamma inverse, this is an element in the Goeritz group, as well as T delta. Okay, so now we want to define the double filtration of the Goeritz group. And so we define this by the following conditions. So we consider the elements in the Goeritz group. So the Mn term of this double filtration will be given by the elements in the Goeritz group satisfying an infinite number of commutator conditions. And the first thing that we can obtain about this is that, in fact, we only need two conditions in the definition. So we only need to see what happened with K10 and K01. And this allows us to show that G00 is the Goeritz group, and we can also show that they are normal subgroups, and moreover, that they behave very well with respect to the commutator operation. And now we want to extend this double filtration of the Goeritz group to the whole mapping class group. So what we do is that first we extend the double lower central series as follows. So here we have the double lower central series, and we take this column and we repeat here an infinite number of times. And we take this row and we repeat an infinite number of times. And here, everywhere, we have K00. And by using this extension, we can define the following subgroup of the mapping class group. So we have the elements in the mapping class group satisfying an infinite number of conditions. So there is a typo here, is n here. And as in the case of the double filtration for the Goeritz group, so we only need 4 conditions. So we need for the 2 base steps, K10, K01, but we also need to add the condition for the inverse. And the second property is that this filtration becomes interested only for integers greater or equal than -1. And of course, by definition, it coincides for non-negative integers, it coincides with the double filtration of the Goeritz group, and we can identify the leading terms. So we have something like this. So we have here the double filtration for the Goeritz group, and here we have the extension for the mapping class group, and we can identify the leading terms. So we have the twist groups here, and the 2 handle body groups here, and the mapping class group. Now let me tell some words about the relation with the usual Johnson filtration. So here we have the Johnson filtration, which is defined using the lower central series. And here we have the double Johnson filtration defined using the double lower central series. So by definition, we are going to have that the mn term of the double Johnson filtration is contained in the m plus n term of the Johnson filtration. So for instance, all this diagonal is contained in the first term of the Johnson filtration, which is the Torelli group. All this diagonal is contained in the second term of the Johnson filtration, which is called the Johnson subgroup, and so on. But moreover, we can show that the Torelli group can be written as the product of the 4 terms in the first diagonal, but we need to add the second term in the Johnson filtration. But we conjecture, in fact, that this group is contained in this product of groups. And therefore, we will have a decomposition of the Torelli group as the product of 4 groups. And this, so all this can be done also in an abstract setting. In particular, we can do this for the automorphism group of a free group. So we consider a free group on P plus Q generators. So we split the set of generators into sets. And we can define a similar filtration, a similar double filtration for the automorphism group of this free group. And if we consider the analogous of the Torelli group, so the elements which act trivially on the abelianization, so this group can be written as the product of the 4 subgroups of the double filtration appearing in the first diagonal. Okay, so this is more or less the reason, because we expect that is also the case for the Torelli group. And so we can do this more easily because we know a explicit set of generators for this group. Also, we know for the Torelli group, but they are more complicated to work with. So for instance, in genus 3, we have 43 generators, so they are very complicated. So to show this theorem, we need to use different kind of tools, and that we use is the Johnson homomorphism. So I will stop here, and thank you very much for your attention.
Thank you very much, Anderson. If people want to hit their